So in this lecture, we're going to cover a reaction called the Robinson annulation. We're just going to focus on this reaction, but it's a fairly sophisticated mechanism, or it involves a fairly sophisticated mechanism. But it really ties together all the things we've been talking about so far related to carbonyl chemistry: enolate formation, Michael reactions, aldol condensation reactions. All of them get tied together in this one reaction to make an important six-membered ring. Okay, so Robinson is Sir Robert Robinson. It turns out that he was a prolific chemist and was actually knighted. So, I don't know, fun facts, I guess. Okay, let's get into it. So in this reaction, what we're going to do is react an alpha-beta unsaturated carbonyl that has a CH3 at the opposite end of the carbonyl with some other, typically an aldehyde. So if we have R1 and here's R2, it's important that the R1 side of things have two alpha hydrogens. We're going to react these under basic conditions to give rise to a final product that looks like this. We're going to have an alpha beta unsaturated carbonyl. We have R1 over here now and R2 over here. So quite the transformation that occurs here. We're going to form a ring, get back our site of unsaturation, but the original one is long gone, seemingly. Okay. So what's happening here? Well, overall, the mechanism, being a complicated mechanism, I again like to know the stages so that I can study the stages before I worry about memorizing every single curly arrow and that sort of thing, because it doesn't work. Know the stages, and then that can help you guide the curly arrows if you make informed choices. So stage one, we're going to form the enolate. And this is going to be the first enolate formation. So I'm going to call this enolate formation 1 on the saturated, I'm going to call it aldehyde, or saturated carbonyl. So the saturated carbonyl is not going to have the double bond. In step 2, we're going to do the Michael reaction. Okay, and then step 3, and this is going to be conjugate addition, I should add. Then step 3, we're going to have a second enolate formation. And this is going to be with the CH3. So the CH3 that I highlighted in the original structures is going to get involved at this stage of the game. And then number 4, we're going to do a last aldol condensation to form the product. So if you look, it's really kind of a Michael reaction than an aldol condensation, with something going on with enolate formations along the way. So it's really just those two reactions, because every Michael, well, not every Michael, it's just a Michael reaction where the nucleophile is an enolate. Okay, anyway, let's get into it. So the mechanism looks like this. We're going to take the hydroxide and first engage the saturated carbonyl. That's that carbonyl that I had reacting with the R1 group. It's got, well, both of the partners have alpha hydrogens. It's these alpha hydrogens that we have to pull first to give rise to the desired product. And I'm just going to draw the enolate structure without the resonance contributor just to get here. So this is enolate 1. Okay, so this is step 1. So far, so good. Oops, sorry, pages. So I've got my first enolate, and now I need to engage that with, should only need a few pages. I'm going to take that first enolate and react that with the alpha beta unsaturated carbonyl in a Michael reaction. Now this isn't a bad reaction, for sure. We've seen this before. It's just, it's a reaction that has some tricks involving bond line structures where we could get lost in terms of where the bonds, how many carbon atoms we had and where the bonds were and that sort of thing. But we're going to have a positive charge here. Shoot, sorry, I need this. Double bond gone, double bond's going to be across here. Okay, so the negative charge is going to add to the positive charge here. Now, when I redraw these products, I want to draw things with as little movement as possible until I've got things well and in hand. So what that's going to look like is we're going to take this top piece. Oops, I'm sorry, I don't mean to have it in blue here. I'm going to take this top piece, R1, Draw a blue bond from the alpha position down to the beta position of the bottom piece, because that's where the connection point was. Okay. Now what we have floating around is some H2O. This was the water that was generated when hydroxide pulled off the alpha hydrogen in stage 1. Okay, so now we're going to do that. Where we grab the hydrogen. Now we're going to pull off the hydrogen from that water and regenerate hydroxide to make the next enolate. Okay. That should now complete stage 2. So far we've just kind of did a funky Michael reaction with an oddly drawn nucleophile. Okay, and we looked at enolate addition by way of malanates and the other 1,3-dicarbonyls that I had alluded to in the last lecture. So what's happening here? Well, now we're going to take advantage of this hydroxide, which is going to pick off the alpha hydrogen of the CH3 group. I'm just going to redraw this entire intermediate just to keep the stages separate. So stage 3, I'm going to take this structure. I'm going to highlight the CH3. Okay, so the hydroxide is going to add to the CH3 and plop one of the, and pull off one of them and leave behind the electrons on that alpha position. That's going to generate the second enolate by involving that CH3 group. Okay. Now what we need to do is let this negative charge that's on the CH3 wrap around and attack the carbonyl that's on the aldehyde. You could, if you wanted to, do a free rotation where we draw this in a more suggestive fashion. So I'm just redrawing this. That's all I'm doing is redrawing this. Okay, that's all I've done is just redrawn this. I've rotated 2 bonds to get to this species. Now, if you look, the R1 and the R2 are in close proximity, but now even more importantly, when I have that negative charge reach around and attack, you're not probably too bothered by this resulting structure where I comfortably have things positioned in a 6-membered ring. Okay, so when this hydroxide picked off one of the hydrogens from CH3, we formed water. Now that water is going to come back into play here, or some sort of other alcohol solvent that's around serving as a base. Okay, so we're going to pick off that hydrogen here to make an alcohol. That's going to give rise to this species plus the OH minus. Now, if you look, we've done an aldol reaction, not a condensation, but rather a reaction. And I said this ends up with an aldol condensation. We're going to do the aldol condensation under base conditions, where the hydroxide goes back and does some more work, where it ultimately generates water and then it stays put its water. It's like, I'm done. I'm forming water. Well, what that gives us is a negative charge that's going to sit around ever so briefly before it adds in to make an alpha beta unsaturated carbonyl and then kicks off the OH minus. So that negative charge that's generated is an intermediate along the way for an elimination reaction that gives rise to more hydroxide that can promote more of this reaction. Well, we generated the H2O previously, but anyway, this is our E1CB condensation, where under basic conditions, we form a negative charge that's stabilized, so it's going to hang around for a second, not a second, like a little bit, before pushing off the OH minus and completing the formation of our double bond, and there we have product. Anyway, I'll let you decide if you think Sir Robert Robinson deserved to be knighted for this reaction. It's pretty cool from my my vantage point. I like this reaction, and that's why I like to talk about it at this point in the semester. But anyway, that's the Robinson annulation, kind of trying to synthesize all of these reactions we've learned together. And it's a great kind of capping point before we get into carboxylic acids and their derivatives to kind of move us into some biological chemistry and that sort of thing. But anyway, that'll do it for this lecture. So, that's it for now. We'll see you next time.